Hello everyone, my name is Florent Teichteil-Königsbuch. I am a senior artificial intelligence scientist working in Airbus Artificial Intelligence Research Lab. Today, I will speak about challenges and lessons learned from planning and scheduling problems in aerospace applications when only simulators of the system's dynamics are available. First, let me introduce you to some typical aerospace problems and see if you can guess what is common to all those applications. Let's begin with an Earth observation agile satellite mission, where priorities are assigned to imaging requests from different clients on Earth. Each request is composed of hundreds of meshes and there are more than 5,000 requests to handle at any moment in the backlog. For a given assignment of request priorities and a set of historical seasonal cloud coverage forecasts, a scheduling algorithm decides for each weather scenario when to acquire a given request mesh. Our objective south is to reason about a meta-problem consisted in dynamically choosing, several times per orbit, the best priority change of each request so as to minimize the average overall delay of delivering images to clients. This can be modeled as a Markov decision process, where actions are simultaneous request changes and uncertainties come from historical weather forecast variations. Our second application is a probabilistic flight planning problem under uncertain weather and traffic conditions. Given a set of ensemble weather forecasts for the day and different traffic predictions built from historical weather-dependent statistical analysis, we must compute a flight planning policy that decides the next waypoint, altitude and speed of the aircraft in order to minimize the average fuel burn or flight time spent in hazardous weather areas. The policy must also ensure that the aircraft can land with a minimal safety fuel reserve and within a given time window so as to respect the airline's schedule. This problem can be modeled as a constraint stochastic shortest-path problem. Our third application is about synthesizing a fully autonomous controller of flying or taxiing aircraft's raw actuator inputs from raw sensor outputs. Actions and states are composed of hybrid discrete continuous variables. The dynamics of the state changes are governed by many coupled aircraft subsystems differential equations. This problem can be formally modeled as a deterministic Markov decision process. Finally, our fourth example problem is more futuristic. It ambitions to provide an holistic end-to-end autonomous assistance to manufacturing workers. Blue collars would be assisted by robots assessing the situation using vision and interacting with humans using natural language. White collars would be advised by an autonomous workflow optimizer of any required change to the global schedule so as to minimize delay or overspending risks. Such an application would rely on a variety of AI decision-making techniques ranging from robotic control to probabilistic scheduling. So let's be positive. All those applications can be modeled as control, planning, or scheduling problems. However, they highlight a bunch of challenges for the community. First, there is no model of the state transition function, but only simulators of satellite motion and orbital physics, aircraft physics and performance evaluation, robot motion, manufacturing workflow, weather dynamics. Moreover, a single state transition step of the simulators takes significant CPU times, about 100 milliseconds for the aircraft dynamics, 1 second for evaluating the aircraft performance, 10 seconds for satellite applications. Note that many thousands of transitions must be simulated to properly compute a plan, a schedule, or a policy. Furthermore, in many cases, simulators cannot be one started from any given random state that a search algorithm would explore. For instance, weather prediction models can only be deterministically rollouted from different sampled initial conditions. Physics simulators internally maintain a very complex state that is not available to the planner, which prevents us from restarting the simulator from any possible given state. Finally, in most cases, there is no non-heuristics, neither informative nor admissible, that could be used to guide search algorithms. This is due to the complexity of the underlying state space topology and to the lack of a relaxed transition graph model at hand. So at this point, the situation seems a bit desperate since most research works on planning and scheduling make assumptions that are wrong in all the presented examples. Existence of a white box transition function model, quick generation of transitions from random search states, availability or computability of heuristics. However, the real problems are what they are. The issue is often the way we look upon them. Fortunately, or perhaps pragmatically, since in industrial environments problems must find solutions, some well-known techniques or tricks can come to rescue. For instance, we can use approximate transitions models or roll out simulation-based approaches. Let me give you some examples. In the probabilistic flight planning problem under uncertain weather and traffic, generating the aircraft and weather state at the next flight waypoint relies on two simulation blocks. First, we must simulate the aircraft allowed speed and altitude at the next waypoint, as well as its fuel consumption. This simulation integrates complex differential equations that can be approximated with a much simpler tabular Banach model. Second, the simulation must find out what are the possible weathers at the next waypoint. However, there is no Markovian model of probabilistic weather predictions based on aircraft-centered local observations. Even a global Markovian probabilistic weather prediction model would be difficult to compute, since uncertain weathers are computed by weather providers as independent weather scenarios from different sampled initial weather conditions. That said, we can statistically approximate ensemble weather forecasts by pretending they are Markovian, but losing spatiotemporal interactions between adjacent weather observation points. Doing so, we can model an approximate probabilistic state transition function that can fit standard search or operations research techniques. If you want to know more, please look at the paper mentioned below that is presented this year at ICAPS. In this second example, we look at the Earth observation mission planning problem under uncertain cloud coverage. Generating the satellite and environment state at the decision points requires on one hand to simulate the satellite's flight dynamics and image acquisition progression, which takes several seconds of computation for every single simulation step. On the other hand, we must simulate possible cloud coverages at the next decision point, narrowing several years of historical weather data. As explained in the previous slide, there is no easily computable Markovian local model of weather forecast, leaving us with the only solution of rollouting sampled scenarios from different historical weather observations. In addition, it is worth mentioning that this problem's branching factor is so huge that it is out of reach of most search algorithms. The solution we propose in the paper mentioned below, which was presented last year at GECO, consists in running different rollouts where the weather scenario and the priorities allocations are fixed for each rollout, and priorities allocations are optimized in each rollout by using a genetic algorithm. The third example is the synthesis of aircraft flying and taxiing controllers by interacting with a realistic simulator of the aircraft subsystems. The simulator updates the aircraft sensors according to the actuator's inputs, atmospheric conditions, and differential equations of the aircraft subsystems. The interaction between the subsystems is so complex that there is no model of the global state transition function. Moreover, the state and action variables are hybrid discrete continuous, preventing us from building a complete reachable search grid. The simulator's internal state is itself scattered in the form of local variables everywhere in the subsystem simulation functions. It can be only partially get or set, preventing us from deterministically one-starting the simulator from any given state. As a result, the simulator can only roll out full state trajectories starting from the initial state. Our solution, which will be presented at ICAPS later this year, is based on a variant of rollout iterated widths adapted to hybrid discrete continuous state spaces. The benefit of width-based planners, contrary to search-based heuristic planners, is that they do not need the knowledge of the transition function, but only the state variables and additional optional features to guide the search. They are especially well suited to tackle simulation-based domains, but they require us to be able to map state variables to some discrete feature vector. Our encoding of the continuous variables, which is based on counting state variable values expansions, arouses the algorithm's curiosity by incentivizing it to push the boundaries of the explored state variable values while pruning already explored state variable values intervals. To conclude this presentation, I would like to underline the main features and challenges of many aerospace planning and scheduling applications. The state transition function is a black box that uses complex simulation engines. Each simulation step is CPU demanding, up to tens of seconds for a single simulation step. In many cases, the simulations cannot be one-started from random search states. There is generally no informative nor easily computable heuristics, despite huge branching factors that call for efficient pruning mechanisms. Let's be lucid and honest. Only one of those features rules out most existing search algorithms. On the other side, blind reinforcement learning, or most rollout-based search algorithms, cannot handle the combinatorics, the frugal access to transition samples, and the sparse reward structure of those problems. We think industrial aerospace problems raise great research challenges that highlight the need for simulation-based search algorithms. Thanks for listening.